Hey there, Calc 2 folks, back here with my last lecture in this set of lectures looking at the calculus of polar curves and equations, where we have looked at slope of the line tangent to a polar curve, we've looked at area trapped within polar curves, and then lastly here we need to look at the arc length of polar curves, right? Where to begin with, we are going to kind of start in with our proof here to begin with in this set of notes. And we start with what we understand in terms of arc length in the rectangular coordinate system. All right, and this does come back from the beginning of the semester. I think it was around section 6.5 where we looked at arc length in the polar coordinate system. Right, no, was that 6.5 or 6.6? Somewhere back there in chapter 6, though, when we were looking at application of integration, we introduced this calculation here, where we consider having the length of the curve, y equals f of x in the rectangular coordinate system, over values of x from a to b. And we had found that that calculation is equal to the integral from a to b with respect to function x, all occurring on this integrand given by the square root of 1 plus f prime of x quantity squared. All right, this should be a familiar calculation. Now, what we may need to recall is where it came from, right? Recall where this developed from as a calculation is this value of L, right? Which is equal to the limit of this Riemann summation, this summation that occurred on the square root of the value delta x squared plus delta y squared, where delta x and delta y were changes in x and y with respect to the change along our curve, right? For values of x from a to b in value, all right? Where this definition here, right, can actually be expressed using the definition of the definite integral, right, which would allow us to go about saying that this value of L that we see stated in this manner here, right, on the for the limit of this Riemann summation of the square root of delta x squared plus delta y squared, that value must be equal to then an integration, where here we see that the limit of the summation will become the integration from alpha to beta for what is going to be the integrand given here by the square root of delta x squared plus delta y squared, where in our interpretation of the definite integral turns into the square root of dx squared plus dy squared. Where we do take note in this statement here, right, we don't have a differential, right, coming out of some delta value at the end of our limit of the Riemann summation here, right? We don't have some delta value here that turns into some d value. Here specifically the d value with respect to these angle measurements from alpha to beta, or here we have a to b. Right? I have to make, I think, an adjustment there. I'll go back and do that before I publish. I think I make it down a little further in the notes, where what we are going to do here is we are going to incorporate some differential into this argument by using the differential d theta over d theta, which is just like multiplying this result of the integrand by the value of 1. Now, when I multiply by this value of 1, it doesn't change its value at all, right? Where I am going to leave this differential with respect to theta outside the radical and take the 1 found in the denominator and move it inside the radical symbol. And when I move it inside, it is going to square itself, and then those squares will distribute to both terms in these squared values, where when placed d theta over d theta squared, and this is placed over d theta squared, we can write this as dx d theta squared plus dy d theta quantity squared. And we have now incorporated d theta into our integration. where in the polar coordinate system, right, for values of r equal to f of theta over theta in the interval from alpha to beta, right, we know x equals f of theta cosine theta, and we know y equals f of theta sine theta when parameterized in terms of the value theta, implying that when we think of their first derivatives, dx d theta and dy d theta, we have these results that we encountered back in our calculation for the slope of the tangent line, where we can substitute into this statement for dx d theta this quantity, and we can substitute into this statement for dy d theta this entire quantity. And when those are substituted in, the above value for L, which we have stated this way, can be expressed this way in terms of theta. In terms of theta, where we might say we're now integrating theta from alpha to beta, where when we substitute these quantities into these quantities being squared, we are going to have to square those quantities along the way. And when we square those quantities, we do get some simplification that happens. And I am a little quick here in the simplification, but we will get a square out here and a square out here, where you will have some common factors in both of these terms, not common factors, some common terms in both of these terms, or I really say opposite terms, come out from these two squarings that cancel with each other. And then when canceled with each other, we should be able to regroup these involving this group and this group, where in each of those groups you will notice you have f of theta squared times a cosine squared theta plus an f of theta squared sine squared theta that you can factor f of theta squared from. And here you have a similar looking statement that involves f prime of theta squared that you can factor f prime of theta squared from each of these terms. And when you do that in both cases, you'll be left with cosine squared theta plus sine squared theta, or in this term, cosine squared theta plus sine squared theta, which are equivalent to 1 in value. So when the value under the radical simplifies further, right, by grouping and then converting the cosine squared theta, sine squared thetas into the values of 1, we do produce f of theta squared times 1 plus f prime of theta squared times 1 under the radical, where that becomes f of theta squared plus f prime of theta squared d theta. Right? And we have this integration form here with respect to our polar function r equal to f of theta. That does involve our polar function f and does involve its first derivative f prime of theta. Right? Note, this result of L describes the formula for finding the arc length of r equal to f of theta over these values of theta in this closed interval from alpha to beta, and is presented as proof for the following theorem. Right? So folks, that was our proof there of this theorem. Assume we have some polar function that has a continuous first derivative for values of theta in this interval from alpha to beta. Right? The length of f over these values of theta is given by the formula we derived above. Right? Or if we consider the arc length then for a case of r equal to 2 sine theta over values of theta in the interval from 0 to pi, this polar curve will be illustrated as follows. It will be given by this circle here over these values of theta in the interval from 0 to pi, where we might note r equals 2 sine theta is our function f of theta. It goes into our formula here. Its first derivative would be 2 cosine theta, which would go into our formula here. And those quantities squared would produce 4 sine squared theta plus 4 cosine squared theta, involving that common factor of 4, which when factored from sine squared theta plus cosine squared theta, right, leaves the value of 1 in that factor. So you end up with 4 times the quantity 1, equivalent to 4 sine squared theta plus 4 cosine squared theta, which is nothing more than the value of 4 under the radical, so it's the square root of 4, which is 2, a constant multiple you could bring out in front, and you really are just integrating from 0 to pi with respect to theta, where your argument inside here, you might say, is still that value of 1. Let me get back down there. All right, we might point it out that way. Where when I integrate now with respect to 1, well, that is just, well, if you integrate 1 with respect to theta, that is just the value of theta, that when you now evaluate across the bounds from 0 to pi, you get pi, right, which simplifies to 2 times pi units in length, right, when you multiply by that constant multiple of 2. Now, 2 pi units in length is the length of this polar curve seen above. This polar curve given by r equal to 2 sine theta. And it was calculated using this integral calculation. Now, you will notice that that polar curve is nothing more than a circle with a radius of 1, right? Where, recall, for the circumference of a circle, well, that is just 2 pi r in value, where if we have a radius of 1, that would be 2 pi times 1, or 2 pi units in circumference. So the circumference formula for this circle does align with what we got in our calculation here or what we obtained in our calculation here for this integration. Right? So folks, that is arc length of polar functions. Now I will tell you that just like our arc length calculation back here in the rectangular context, these integrations can be rather tricky at times, and are the cases where sometimes we have to rely on other rules or techniques to form their calculations. These often have to be unique in terms of their setup to be calculated. These are not integrals that always are nice in calculation. So be careful as you move forward here trying to practice some of these skills off without, maybe looking at the book or using some other given examples where it's been worked out ahead of time that the calculation is something that is doable with the skills that you have. If not, you may need to rely on things like Mathematica and whatnot to come up with approximations of those values, right? Or some other approximation technique. Now, that is, like I said, arc length, the polar curves. This section of material in combination with arc length, or slope of the line, tangent to a polar curve, and area trapped within polar curves kind of makes up that calculus of polar curves, right? The calculus that occurs in the polar coordinate system. All right? So, folks, with that said, we are kind of finishing up our study of the polar coordinate system. Keep in mind these chapter 12 topics, or these topics of the parametric system, the polar coordinate system, and what we're going to discover in our next idea here, the conic sections, are all topics that are going to come back to us in Calc 3, right? My Calc 3 students right now are studying multiple integration, or have wrapped up their study of multiple integration, where they have relied heavily at times on the polar coordinate system to help define some of these regions over which they're integrating. Now, none of that may make sense to you right now, but when you get up into Calc 3, you're going to note how all of these topics from these last few lectures and future lectures are all going to relate. So, folks, with that said, I hope you're out there keeping on top of everything and studying these ideas, and I will be back with my next set of videos covering the conic sections. I don't know how I'm going to do those yet. If I'm going to do those, I'll probably approach those with little videos here. It's getting to be long to put these to kind of try to combine all these videos into one talk. So I have kind of broken them up here and done them throughout a day, because it does get long doing a single video that might go on for an hour and 15 minutes. So the easiest way for me to approach it is maybe to break them down a little bit, and that's what you see happening here. I'll probably continue doing that, just to give you a heads up. But I hope you're all well. I hope you're hanging in there. hope you're maintaining social distancing. I think we're on the end of week 6, folks. Do the math, right? That's a lot of days, 42 days sitting around for some of you. For me, I know I haven't left the house in quite a while to do much other than go over and check on my parents every now and again. But other than that, I've been sitting at home, having groceries delivered and everything. So, yeah, it's a little long. I can say that. But I'll keep these videos coming. They keep me sane, and I'll see y'all next time.